This is lecture 19 of a class called Numerical Methods at Bethel University in St. Paul, Minnesota. It's basically equivalent to classes called Numerical Analysis at many other schools, very similar subjects. Lecture 19 you can see is about data approximation and something called Neville's method. Lecture 18 was about Lagrange interpolating polynomials, and you want to make sure you understand that concept before you learn about Neville's method. Neville's method is pretty challenging to understand. Actually, usually I recommend reading the textbook, and here's our textbook, Numerical Analysis here, before watching a lecture on a subject. However, this subject is so hard to understand at first in general that it's definitely easier to understand particular examples, and so I'm recommending to my students that they watch the lecture before they do the reading. So here's the plan. First we'll talk about Neville's method for an example with 3 data points. It's the simplest possible situation. We're going to build up the general iterative scheme step by step, so to speak. We'll start with 3 Lagrange polynomials of degree 0, which really means constant functions. Then 2 Lagrange polynomials of degree 1, those will be linear functions. And then finally 1 Lagrange polynomial of degree 2, that'll be a quadratic approximation. We will emphasize the concepts, okay? Especially the computational iteration scheme and where that comes from. We'll think about the geometric interpretation of the formulas as weighted averages. We're not going to really prove things so much as just think of it intuitively in terms of weighted averages. And we'll make graphs of our results. Now, I should say also at the outset here that Neville's method is really set up mostly to do computations with particular numbers and not necessarily formulas. That's its main benefit, in fact. However, we will talk about formulas as part of the discussion here. Then that will lead to the general formula for Neville's method. Again, it's an iterative scheme with a recursive kind of formula. We'll see that that formula is best thought about in a tabular environment with certain notational conventions. Actually, we'll talk about the notational conventions from the textbook at first with the simple example, but then once we get to the general situation, we'll talk about the more general kind of convention. We will then apply Neville's method to the sine function using 5 data points. Then we'll implement it on a spreadsheet. This is doable, though not really ideal. It's not quite as ideal as you might like, unless the nodes that you use, the x-coordinates of the data points, happen to be equidistant from each other in the x direction. Then it is more ideal. Finally, we'll do a sample exam problem by hand that I have given in the past. Okay, so that is the plan. Again, this is a tough topic. You really need to concentrate hard if you're going to understand this and then be able to apply it. And it's again the notation that gets pretty messy. So let's build it up with an example here. Neville's method with 3 data points. It's page 1 of that. So here are the 3 data points. Here's one notational convention, is that the first data point we actually label with a subscript of 0. And I will typically call that the 0th data point, even though it's the first. The second data point we label with a subscript of 1, and I will typically call that the first data point, even though it's the second. And the third data point we typically label with a subscript of 2, and I'll typically call it the second data point, even though it's really the third. Okay? The nodes themselves are the x-coordinates you see here, 2, 4, and 6. And then these other numbers, the 5, 6, the 8, those are the second coordinates. Those are the functional outputs for some unknown underlying function f of x. Now, this method only works reasonably well when f of x is kind of a nice function. If it's a wildly oscillating function, this is not really a good method to use. Okay? So you need to have some sort of physical basis to believe that the function is a relatively tame function. Our goal is to ultimately estimate f at a particular value of x between 2 and 6, and I happen to pick 4.5. I could have picked something different here. All right, so let's build up the method with simple pieces, and we're going to build to more complex but more accurate pieces. And pay attention to this notation. We're going to let p sub 0 of x, p sub 1 of x, and p sub 2 of x be the constant degree 0 polynomials. They're constant functions that agree with these data at respectively the nodes x0, x1, and x2. So the subscript refers to the node that it agrees with the data at. That's very important to keep track of. So p0 of x is the constant function y0, which is 5. P1 of x is the constant function y1, which is 6, and P2 of x is the constant function y2, which is 8. Okay, and the graphs of these are going to be horizontal lines. These are taken to be true for all x, and then in any particular x, like 4.5, we could use these as approximations for f of 4.5, though obviously not necessarily a very good approximation. We can make graphs of these things. Here they are. They're horizontal lines. So P0 of x is the red graph. That's 5. P1 of x is the blue graph. That's always equal to 6. And P2 of x is the pink graph. That's always equal to 8. And x is 4.5. That's where we're trying to approximate the underlying function at. And these different graphs gives us different approximations of 5, 6, and 8. Okay? So kind of a silly thing to do, you might say, but we're trying to build up to the more general and hopefully more accurate kind of situation. All right, go on to page 2 here of Neville's method with 3 data points. So we're going to now go on to linear functions that are not constant. P sub 0, 1 of x is going to be a degree 1 Lagrange interpolating polynomial that agrees with the data points at the 0th and 1st nodes, which are really, again, the 1st and 2nd, x0 and x1. And P1, 2 of x is going to be a linear Lagrange interpolating polynomial that agrees with the data at the second and 3rd points, which are labeled x1 and x2 for the nodes themselves. Okay, so the subscripts again are key here in this notation. Now, I should also say that this notation is not necessarily standard, and if you see a different book, you might see different notation. This is the way our book has chosen to write this, and I think once you get used to it, it's not too bad. So again, the first one, the P01, agrees at the nodes x0 and x1, which are 2 and 4. And the second, the P1, 2 of x, agrees at the 1st and 2nd nodes, which again are really the 2nd and 3rds, x1 equals 4 and x2 equals 6. And let's not forget that f of 2 is 5, f of 4 is 6, and f of 8, those are the second coordinates of the data points. That'll be helpful in looking at the next equation. Right here, this is the Lagrange interpolating polynomial based on what I talked about in lecture 18 that's going to agree with the data at the 0th and 1st nodes. 5 is the output of the function at the 0th node, which is 2. 6 is the output of the function at the 1st node, which is 4. F of 2 is 5, f of 4 is 6. Notice with this first term here, this is a linear function which equals 0 when x is 4, which is this node, the 1st node, which again is really the 2nd, and equal to 1 when x equals 2, the 0th node. 2 minus 4 over 2 minus 4 is 1. So when it's equal to 1, when x is equal to 2, then this entire expression, including the 5, is equal to 5 times 1, or 5. It equals the original function when x equals 2 and is 0 when x is 4. On the other hand, this term right here is 0 when x is 2 and 6 times 1, which is 6 when x is 4. This term agrees with the function at the 0th node. This term agrees with the function at the 1st node. Now I'm going to do something a little weird that you can see here. I'm going to rewrite this in kind of a weird way. I'm first going to combine these as one fraction. This is definitely worthwhile to do because it's going to generalize to Neville's method. I'm going to rearrange. I'm going to put the x minus 2 and the 6 over here first. Put the x minus 4 and the 5 over here second, except with a minus sign. Why did I put a minus sign there? Well, so that I can keep the bottom the same for both of these things. This is 2 minus 4 over here. This is 4 minus 2 over here. If I'm going to make it a 4 minus 2 when I combine the fractions, I need a minus sign there. I also could put a plus sign there and then make this a 4 minus x in here, but our book makes a minus sign there and an x minus 4 here. I should warn my students, however, that at the bottom of, I forgot what page it is in this book, there's a bad typo in a few spots. There's a plus sign put there instead of a minus sign. I will send you a note about that in this book. Oh, maybe I should look up the page quick. It's page, the bottom of page 117. I don't know if you can see this. I made notes to myself here. These, you see some equations there that look similar to these with plus signs in the middle. They should be minus signs. So bad typos there. You need a minus sign here on page 117 at the bottom if you want to be consistent with the way the book talks about it in general. Remember that 6 is really P1 of x, that constant function at the 1st node. And 5 is P0 of x, the constant function at the 0th node. So yet another way to write it. And if you simplify all this, whether you think about it here or this way, it simplifies to 0.5x plus 4. Okay? What about the other Lagrange interpolating polynomial for the nodes x1 equals 4 and x2 equals 6? It's this. You got the output of the function at 4, at x1, which is 6, times an expression which equals 0 when x, careful, is x2, which is also 6. These 6's, in a sense, come from different places here. And equals 1 when x equals x1, which is 4. 4 minus 6 over 4 minus 6 is 1, times 6 is 6. This is an expression that agrees with the original function at x1, which is 4. Its output is 6 there, and is 0 at x2 equals 6. On the other hand, this expression here equals the function 8 equals 8 at x2 equals 6, and equals 0 at x1 equals 4. That would be a linear function that interpolates those 2 points. Once again, I can rewrite it in kind of a funny way. I can put the 8 in this x minus 4 first here, like this, and the 6 in the x minus 6 like that over here with a minus sign there because I want the denominator there, 6 minus 4, to be constant when I combine these fractions, and this one's 4 minus 6, so I'm switching those around and putting a minus sign there. Again, 8 is the same as the constant function p2 of x, 6 is the same as the constant function p1 of x, and if you simplify this, it simplifies to x plus 2, okay, no matter how you think about it. This is definitely worth doing to generalize to Neville's method. Furthermore, we can go ahead and plug in our value of x that we're interested in, x equals 4.5 into both of these things. P0, 1 of 4.5 is 6.25. You could double check that here. 4.5 times 0.5 is 2.25, plus 4 would be 6.25. You plug in 4.5 into this one, you're going to get 4.5 plus 2 is 6.5, like you see. These are getting pretty close together. And in a sense, they're both reasonable estimates for f of 4.5. Think about just the outputs here between x equals 4 and x equals 6. The outputs are 6 and 8. These reasonable estimates should be between 6 and 8, and probably closer to 6 than to 8 because 4.5 is closer to 4 than it is to 6. Okay, real key kinds of things to think about to understand this conceptually. All right, on to page 3. There's 7 pages to this part. Hang with me. This is really key to understanding it. Also notice, okay, again, kind of a weird looking thing that I'm doing here, that the output at 4.5, 6.25 is P01 of 4.5, can be thought of as this expression here, which I'm calling a weighted average. Okay, what did I do? I went back to the equation on the previous slide. I plugged in x equals 4.5 in place of the x. So this was x minus 2 was x0 times f of 4, which was 6, f of x1, minus, in parentheses here, x again, minus x1, which was 4, times f of 2, f of x0, which was 5, divided by x1 minus x0. If you take this expression here, for example, and you know, the 6 right there, that's the f of 4 right here. F of 4 is 6. Take 4.5 minus 2, you get 2.5. Divide by 2. 2.5 divided by 2 is 1.25. That is the weight in front of f of 4. And then with the f of 2 being 5, it has a weight of negative 0.25. Why negative 0.25? Well, take this thing, 4.5 minus 4 to get 0.5. Include the minus sign. Negative 0.5 divided by 2 is negative 0.25. Now, that's kind of a weird weighted average. What makes it a weighted average? These coefficients, these weights, the 1.25 and the negative 0.25 have to add up to 1. That's one thing that makes it a weighted average. And why do we have these weights? Why does f of 4 get a weight of 1.25 and f of 2 get a weight of negative 0.25? Well, it's because the input, 4.5, is to the right of 4. It's closer to 4 certainly than to 2. We should give f of 4 a lot more weight in a sense if we're trying to approximate the function at 4.5 than we should f of 2. Why should it have a negative weighted f of 2? Well, partially it's to make those coefficients add up to 1. And partially it's because of a picture that we see here. And actually I tried to make this an animated picture and I'm not sure why it's not running the animation. It was running the animation before. Let's see here. Maybe if I do this, there we go. Maybe it just didn't like my pen tool being used. There's an animation showing how when the coefficients of, well, here it's 4 and 2, not f of 4 and f of 2. We're looking at the inputs here in this equation. Here we're looking at the outputs. So I'm thinking about the x values. I'm thinking about the inputs here. I've got the 0th node, x0 equals 2, the first node, x1 equals 4, and then I've got x equals 4.5 in green here. That's where I'm trying to evaluate the function. When that red dot is at that green point here, you see that the coefficients of the 4 and the 2 are, well, okay, now it stalled it again, are 1.25 and negative 0.25. And again, you can double check 1.25 times 4 is 5 and negative 0.25 times 2 is negative 0.5. You do get 4.5. But notice what happens when the red dot is at other spots. When, for example, the red dot is between 2 and 4, the coefficients of both the 4 and the 2 are positive, like right now and right now. And in fact, if you watch it very carefully, when the dot is, for example, close to 4 but just less than 4, like right now, the coefficient of 4 is close to 1, and the coefficient of 2 is close to 0, like right now. And right now. There's a way to think about this geometrically as well. When you're between 2 and 4, for example, say you're at 3.5. If the red dot was at 3.5, the coefficient of the 4 should be 0.75 because you're 75% of the way from 2 to 4. And the coefficient of the 2 should be 0.25 because, in a sense, you're 25% of the way from 4 to 2. And you can double check that 0.75 times 4 plus 0.25 times 2 is 3.5. Okay, it really does work. It's a geometric way to think about this. We'll think about it with other examples here too. Get my pen back here. Let's think about it with the other polynomial, the P12 of 4.5. Its output at 4.5 is 6.5. Once again, you can plug in x equals 4.5 into that equation from the previous slide and rewrite this expression as a weighted average. Again, what makes it a weighted average of these two numbers, f of 6 and f of 4, which are 8 and 6, is because these coefficients add up to 1. Here they're both positive. And so why are these function outputs getting these weights? It's because the corresponding inputs, if you give them the same weights, give you a combination that equals 4.5, the number we're plugging into the function. You can visualize that too. When you're at the green dot, the coefficient of the 6, these blue points are 4 and 6 now, not 2 and 4. The coefficient of the 6, right, now is 0.25. And the coefficient of the 4 is 0.75 there. You're 25% of the way from 4 to 6 when you're at the green dot, which is 4.5, and you're 75% of the way from 6 back down to 4 when you're at the green dot. And likewise, if you're to the left of the 4, the coefficient of the 6 is negative, like right now. And if you're to the right of the 6, the coefficient of the 4 is negative, like right now. And they do combine to give you what you want. You want the f of 4 in this case to get more weight than the f of 6 because 4.5 is closer to 4 than it is to 6. Okay? We'll continue to think about that here. We're on to page 4. Here are graphs illustrating the previous slide. These are the linear functions that are approximating the unknown underlying function f when x is 4.5. Those are the green dots. The outputs are what you see there, 6.25 and 6.5. P01 of x is this red graph. It agrees with the data at x0 equals 2 and x1 equals 4, these two black dots. P12 of x is the blue graph. Subscripts are 1 and 2. It agrees with the data at the first and second node, which are again really second and third nodes. This point here, x1 equals 4 and x2 equals 6. And again, we can use either function, theoretically, to approximate the underlying function. And again, since you don't know the underlying function, you really don't know which of these is more accurate. For sure. You would hope your function's not doing anything too wild, so that both of them are, in a sense, hopefully pretty accurate. But now when we go on to our last polynomial, then we get what we would hope would be the most accurate, though again, it's not really a guarantee. But the notation continues. P sub 0, 1, 2 of x is now going to be a quadratic degree 2 Lagrange polynomial that agrees with all three nodes, agrees with the outputs of the function at all three nodes, the 0th node, the first node, and the second node. That's why we have the 0, 1, 2. Okay? It's going to agree to all three. It's going to be quadratic. In fact, it's going to be unique. Thinking back to lecture 18 about Lagrange polynomials, once again we have this method for constructing them. P0, 1, 2 is a linear combination of three terms where the weights, the 5, the 6, and the 8 are the outputs of the underlying function at the 0th node, the first node, and the second node. 5, 6, and 8 were the outputs, remember. This thing right here, this fraction, is a quantity that equals 0 when x equals 4 or 6, the first node and the second node, and equals 1 when x is 2, the 0th node. Right? Because you get 2 minus 4 divided by 2 minus 4 and a 2 minus 6 divided by 2 minus 6. This would equal 1 there. 5 times 1 is 5. It equals the original function f at the 0th node and is 0 at the other nodes. This one equals the original function at the first node, x1 equals 4, and is 0 at the 0th node, 2, and the second node, 6. And this one equals the original function, 8, at the second node, which is 6, and is 0 at the 0th and first node, which are 2 and 4. And you should take the time to check that this does simplify to this quadratic right here, 0.125x squared minus 0.25x plus 5. Amazingly, and here's kind of the key point to all of this, right here is this amazingly thing. Amazingly, this Lagrange polynomial can be written as a weighted average of the linear polynomials. This is the quadratic, degree 2. It can be written as the same kind of weighted average as before of the first degree ones. Here it is. If you simplify this expression, a linear combination of P1, 2 and P0, 1, where the weights are really x minus x0 over x2 minus x0, and negative, in parentheses, x minus x2 over x2 minus x0. If you go ahead and pause the video and take the time to simplify this, where I'm forgetting the formulas, I think P1, 2 of x was maybe x plus 4 or x plus 2, something like that. I think it was x plus 2. And P0, 1 of x was, I think, 0.5x plus 4. Simplify that, you get the same thing. And that's no accident. These two things are equal to each other. And this is a very similar kind of weighted average that we saw before, just with different notation. Okay, and we're going to try to talk about how to implement this in general. This is no accident. It's a theorem that those are going to be true, equal to each other in general, and this applies to higher and higher degrees as well. You should take the time to check that if g of x is the right-hand side of this expression, this whole thing right here, that g of x0 is equal to the original function value at the 0th node, which is 5, and also equals these other things. G of x2 equals the original function value at the second node. The second node is x2 equals 6. Its output there was 8. And here's the hardest one to verify. G of x1, the middle node, which x1 equals 4, remember, equals 6, which does happen to equal p1 of x1, which is, again, that's by definition of what p1 was. Okay, that's the slightly harder one to verify, but you should take the time to check that. Then you can apply to verify that this g must have to be this. There's something called a theorem that says that the interpolating polynomial is unique. We have a unique interpolating polynomial of degree 2. In general, when you've got 3 points, you're going to have a unique interpolating polynomial of degree less than or equal to 2, but we know it's got to be 2 in this case. Take a breath. More to come here. This is, again, really key to getting this. We can go back to the weighted averages here too. We can think about plugging in 4.5. Oops. P012 of 4.5. If I plug in x equals 4.5 in here and here in the previous slide equation, I can rearrange and write that as a weighted average, where now the weights are 0.625 and 0.375. Those are two numbers that do add up to 1. And it's analogous to the fact that the same kind of linear combination with the same weights of 6 and 2, the second node x2 and the 0th node x0, gives you 4.5. Here's a static diagram to illustrate this. So we got all three nodes in here. x0 equals 2, x1 equals 4, x2 equals 6. We've got the x is 4.5 in green there. 4.5 is 62.5% of the way from 2 to 6. Likewise, 4.5 is 37.5% of the way from 6 down to 2. Okay, and you can double check all these ideas. That's the intuition behind what's going on. It's not a proof of anything, but it's some intuition about why it works. This likely gives us our best estimate for f of 4.5, likely, at least if the function is well behaved, in the absence of other information about f, like if it's some sort of wild function. F of 4.5 is most likely closest to this thing, which turns out to be 6.40625. Okay, you should take the time to double check that. And here's a way to visualize this in a graph. So this red graph is our quadratic. It is our Lagrange interpolating polynomial for the black dots, and when you plug in x equals 4.5, you get an output of 6.40625. In the absence of other information, we imagine for a well-behaved function, this would be our best guess based on these three data points for what f of 4.5 is. All right, let's talk about this in general now. So I'm gonna talk about some way to represent this in tabular form and some alternative notation, actually, that is also in our textbook. Then we'll go on to applying it to the sine function, programming it in a spreadsheet, and doing an example. In general, given n+1 data points, x0, y0, x1, y1, x2, y2, etc., up through xn, yn, for some underlying function, f, and a given number x for which we would like to estimate f of x. And again, I mentioned this at the beginning, ideally with Neville's method, you're trying to apply this without actually finding formulas for the polynomials themselves. You're trying to come up with an algorithm that just deals with the numbers. And that'll be clear when we look at the spreadsheet especially. We are interested in computing the typically n-degree Lagrange polynomial. It could be less than n-degree if some things cancel, but typically it's nth degree. Value p sub 0, 1, 2, 3 through n of x. This would be the Lagrange polynomial notation, emphasizing that it agrees with the underlying function f at all n+1 nodes, x0, x1, x2 through xn. Think of this as a numerical value rather than a formula, though you could think of it as a formula if you wanted to. Here's our general recursive formula for this thing. Yikes, what in the world? Got some weird looking subscripts there. Okay, that's maybe a little too hard to understand without spending a lot of time really thinking about it. Let's go ahead and pick something specific for I and k. I'll pick I to be 10, and which would mean n itself would be greater than or equal to 10, and k to be 6. Let's think about this exact formula in that case. Then we'd be talking about writing p sub 4, 5, 6 through 10 of x, which would agree with the data at nodes x4, x5 through x10, which would be, what, 7 nodes? Okay, so this would be actually then a degree 6 polynomial here, because we're agreeing with it at 7 nodes, based on a weighted average, a linear combination of lower degree ones that agree at 6 nodes and would be degree 5 multiplied by these linear terms. This one agrees with the nodes at the underlying function at nodes 5 through 10. This one agrees at nodes 4 through 9. We take the x value in both cases and subtract, in the first case, x4, the 4th node, which again is really the 5th, and x10, the 10th node, which again is really the 11th, because we started at x0. Those are the coefficients with the minus sign here like before, and we divide by x10 minus x4. Okay, that is this general formula for particular values of I and k. But you should spend a little bit of time thinking about this general formula. But it's going to be easier to remember this stuff if you organize it all in a table. It's best to organize and compute these numbers in a table. Our textbook for my students, again this one right here, also chooses to use an alternative notation at this point, using q's instead of p's, and using just 2 subscripts for every number instead of a bunch of subscripts. And those subscripts correspond to an appropriate entry in the table when it's thought of as a matrix. although the first column and the first row will be thought of really as the 0th column and the 0th row. Yeah. Here's the structure when n equals 4, which means we've got 5 data points. The matrix itself, so to speak, is this part. Oops. Although you see a bunch of blank spots, which you could effectively imagine to be zeros if you wanted to, but you don't need to bother writing them. This would be the matrix that I'm talking about. This would be a 5 by 5 matrix. P0 through P4, those are the degree 0 polynomials, really constant functions, really numbers. And by the way, you can think of all these quantities as either functions or numbers, but when we apply the spreadsheet, for sure, we're going to think of them as numbers. P01, P12, etc. These are the degree 1, first degree ones, linear functions. These things are the quadratics in this column. These things are the cubics, and this would be the 4th degree. I'm alternatively calling these things Q instead of P, and these subscripts correspond to the spot you are in the matrix. 0, 0 means we're in the 0th row and 0th column, row first, column second. 1, 0 means we're in the 1st row and 0th column, which really means 2nd row and 1st column. 2, 0 means 2nd row and 0th column. 3, 0 means 3rd row and 0th column. 4, 0 means 4th row and 0th column, which really means 5th row and 1st column. 1, 1 means 1st row and 1st column, which again really means 2nd row and 2nd column, etc. 4, 1 means 4th row and 1st column, etc. 4, 4 here means 4th row and 4th column, which would really be 5th row and 5th column. That's your alternative notation, and we can rewrite, I'm not going to take the time to do it in the PowerPoint here, we could rewrite the recursive equation, the weighted average, in terms of the Q's instead of the P's. But it's more important to think about it visually. I also add to the table the values of I here and the nodes themselves here. That'll be nice to have in the table as well. Let's look at an example of the sine function before we go to the spreadsheet. Actually, with the spreadsheet, we will re-emphasize the same sine function example. So we're pretending we know our underlying function, the sine function, and when our nodes are between 0.1 and 0.8 here, you know that the sine function is pretty well behaved. Oh, the input's in radians here, by the way. It's going to look about like this. Okay, that'll be the sine function between x is 0.1 and x is 0.8. Label the outputs of these nodes P0, P1, P2, P3, and P4. Our goal this time is to now estimate f of 0.55. I picked a different number. We've got different nodes here from these data. I could have picked something besides 0.55. Notice that I purposely actually picked these nodes to not be equidistant. Distance between x0 and x1 is 0.2. Between x1 and x2 is 0.1. Between x2 and x3 is 0.2, and between x3 and x4 is 0.2. We got one that's just a distance of 0.1. Neville's method does still work, even when your nodes are not equidistant. It makes the programming in the spreadsheet a little harder. Not quite as nice as it would be, but it still works. Step 1, compute the 0th degree column. In other words, plug all these nodes into the sine function. And here's what you're going to get. You might want to take the time to pause the video and double check these things, making sure your calculator is in radian mode before you do. I'm just going to double check one of them. I'm going to double check sine of 0.8, 0.717356. You can see it there. Hopefully, if it's not too blurry. All right. So that's the 0th degree column, the 0th column of the matrix. Next, compute the next column, the 1st degree column, like this. By the way, so I'm doing it column by column. You can construct this matrix row by row as well. Okay, either way is okay. We could just construct this first row, so to speak, right there, if we wanted to. This is the 1st degree column. This is the output of the 1st degree polynomials, Lagrange interpolating polynomials at 0.55, 0.55, which we can get with the recursive formula in this way. Okay, so think about this with me here. We're trying to find, for example, what's in red here, trying to confirm this number, P sub 23 of 0.55. Okay, why is it P sub 23? It's going to be the Lagrange first degree polynomial, which is a linear function that agrees with the original function, the sine function at nodes x2 and x3, which are 0.4 and 0.6. Alternatively, with this notation, the q, we are in the third row in the first column. 0, 1, 2, third row. First column, we start 0 and then go on to 1. And here in blue, this is our old friend, the recursive equation. You plug the 0.55 in here and here. You subtract, this is x2 here, this is x3. Multiply by, this is where it gets a little tricky. So we're taking 0.5, and here's where you want to think about it visually. We're taking the 0.55 minus x2, which is right there, and then we're multiplying by this number, which is not in the same row of the matrix. That's what this number is right there. So you multiply this times this, and then subtract what you get when you take 0.55 minus 0.6 times this one. The 0.3894 is right here. So you're kind of going kitty corner, so to speak, diagonally in the matrix. You take x minus 0.4, 0.55 minus 0.4 times this thing, and then you take x minus 0.6, 0.55 minus 0.6 times this thing. You've got this cross multiplication going on, so to speak. Then divide by x3 minus x2, 0.6 minus 0.4. And you should take the time to check, pause the video, double check that this does equal this. It's possible your numbers could be off a little bit from mine here because of rounding. And in fact, when I did this stuff with my calculator, I got slightly different answers than the spreadsheet when I did the rounding. You might be off in the last spot or two. Don't worry about it too much. You know, you'd maybe round these answers more for your final answers at the end. As another example, this 0.526464, how would that be computed? I'm not actually going to show it here, but let's just talk about it. You'd take x, which is 0.55, minus 0.8. That difference times this number, 0.56464, minus, think about this fraction with the minus sign there, x minus 0.6, 0.55 minus 0.6 times this number, the 0.717356. That would go over here. Divide by 0.8 minus 0.6. In both of the cases, we're dividing by 0.2, but you know, if we had focused on this one instead, we'd be dividing by 0.4 minus 0.3. You'd be dividing by 0.1 instead. Okay, so you do need to pay attention to that kind of thing. Step 3, compute the second degree column. So for example, the thing we're going to focus on is this thing in red here. That would be, so this is the output of the quadratic approximation. When I is 3, it's going to be p sub 1, 2, 3. It's going to agree with the original sine function at nodes x1, x2, and x3, which are 0.3, 0.4, and 0.6. We can also label that q sub 3, 2, 0, 1, 2, third row, and 0, 1, 2 column, second column. And when we compute it, the amazing thing is that, remember that slide where I had the word amazingly in there? Amazingly, we don't have to think about x2. We don't have to think about the 0.4 at all, even though it's going to agree at 0.3, 0.4, and 0.6. Here's what the recursive formula gives you. P of 1, 2, 3 at 0.55, which you can also write as Q32 at 0.55, is there's x in both spots here again, 0.55 here and here. You take the 0.55, start by subtracting the smaller node here, the x1. By the way, these nodes are labeled in order from least to greatest. In general, they don't have to be, especially when we talk about some other methods here to come. They won't necessarily be in order from least to greatest. But here it is, and it usually makes most sense to do that. That's subtracted first, times this number right here, 0.520836. That's right here. So now I'm multiplying 0.55 minus 0.3 times that. The x in my chart here gets to be bigger than before. Then I subtract, don't forget to subtract instead of add, 0.55 times 0.6, 0.55 minus 0.6, that difference times, careful, don't go 2 spots up here, focus on just 1 spot here, 0.530265. That's the extra tricky part of this, is these are going to be 2 apart here, but these are going to be just 1 apart. So once again, you take, and don't forget to divide by 0.6 minus 0.3, right there. Once again, you take x, 0.55, times the smaller node here, that difference times this number, and then minus 0.55 minus 0.6 times this number. Do not go up to that number there. Divide by 0.6 minus 0.3, and you should get this. Take the time to double check that. Okay? We're getting close to being done here. Let's go on to steps. I'm going to combine steps 4 and 5 into one slide here. Compute the 3rd and 4th degree columns. And here's what I get. And I'm going to highlight the red ones again. This one here and this one here. Down here, for example, P1234 of 0.55 is going to be this number. You see it matches here, and notice how it's constructed. 0.55, our x value, minus, now we're using the 1st node and the 4th node here with this notation. Go between 1st and 4th. 0.55 minus 0.3 times this number here. That's going to be the first diagonal. We're always using the previous column for the numbers that go here and here. Minus 0.55 minus the 4th node, 0.8, times this number here, directly above that one by 1 spot. So your x in the diagram looks like that. Divide by 0.08, or 0.8 minus 0.3. Divide by 0.5 here, and you should double check that you get this number. And finally, the last number, which is going to be our quote-unquote best approximation based on a 4th degree Lagrange polynomial interpolation, is going to be this computation. You could label it P01234 at 0.55. In a matrix form, it's Q44 at 0.5. Now I take 0.55 minus 0.1 and multiply times that number. That's right here. And then minus 0.55 times 0.8 times this number is right here. So those get multiplied on that one. And then take all that and divide by 0.8 minus 0.1 that you see here to give us our final, hopefully best approximation of sine of 0.55. And I do believe, I didn't double check this, but I do believe that is the best approximation of sine of 0.55. It doesn't come out exactly on a calculator like this, but it's pretty close. Okay, so now we're going to go onto the spreadsheet and do the same example we just did. Excuse me. And again, it would be more ideal if these nodes were equidistant, because that would make it easier to program the spreadsheet, so to speak. Because the copying and pasting we do, well, with some adjustments, could be done not only vertically, but also horizontally with some appropriate adjustments. Because we keep, if these were all 0.2 apart, we could keep dividing by, in the interpolating formula, the recursive formula, we keep dividing by multiples of 0.2. But we are going to, in one spot at least, have to divide by 0.1 or possibly 0.3 or 0.5. So we do need to be careful here. So the input again is 0.55. What is the value of the sine function there? Equals sine of b1 will give us the output of the sine function there. It's about 0.5222687. You can see more decimal places if we like. I could compare it with the PowerPoint here. Where'd it go? 0.522686565, 0.5226887. So it's like in the 6th place after the decimal that we end up being off a little bit in this 4th degree approximation. All right, what do we have in column C here? These are the values of the function, the sine function at the nodes. So I can just do equals sine of b5, for example, here to get the sine of that number, 0.1. And then I can click and drag the formula down where the b5 will get updated to a b6, a b7, a b8, and a b9, and give me the correct outputs at those values. There's our table, 0.0998, 0.295, blah, blah, blah. Does that match what we see here? Yes, it does look like it's matching those numbers there. Take the time to double check those things here. All right, here's where it starts to get a little tricky. I'm going to be able to put formulas in here that allow me to copy and paste downward. But again, I won't be able to copy and paste to the right. And if I'm going to make use of X, which is in cell B1, in such a way that I can copy and paste downward, I need to use an absolute cell reference that fixes the cell with dollar signs. For example, I could do $B, $1 to fix whatever number happens to be in cell B1, which is 0.55, and then when I click and drag the formula downward, the B1 will stay always a B1. The dollar signs don't mean money here. They fix the cell reference. They make it an absolute cell reference. By the way, another benefit of doing this on a spreadsheet is that I can update the X if I want. Once I got it programmed correctly, so to speak, I could change the X to something else and see how the approximation does as well. In fact, I think I'll do that. So this is X minus, remember the method, we got to take x0 in this case. We're talking about P01 in cell D6 here. X0 without dollar signs, because I want that to get updated as I click and drag the formula downward to being a B6, then a B7, then a B8. Times, go diagonally here, this number, minus, not plus, minus, in parentheses, B1 again with dollar signs, minus x1, which is 0.3, in parentheses, times, go diagonally to this number. End parenthesis, divide by, in parentheses, 0.3 minus 0.1 from cells B6 and B5. Here we go, 0.540, let's double check that. That matches this number right here. Click and drag the formula downward. The other numbers should be correct as well. 0.526, let's see if that's correct. Yes, 0.526464. All right. I'd like to be able to click and drag it to the right, and with modifications, again, if these nodes were equidistant, I probably could do that. But they're not equidistant, so I better just retype from the scratch. B1, because if I thought about dividing by multiples of 0.2, I wouldn't have to always refer to dividing by subtractions from this column. Here I could divide by appropriate multiples of 0.2. That's why it would be easier to program. B1, now I'm talking about P sub I is 2 here, 0, 1, 2. Want it to match at nodes 0, 1, and 2. The smallest in such node is x0. That difference gets multiplied by this number, minus B1 minus this number times this one right here, right? Divide by the difference x2 minus x0. We don't have to bring x1 into the formula at all. That is the amazing thing, that works. Okay, that is the nicest thing about all this, in fact. Okay, so here's what we get, 0.5253339. Looks good. Click and drag that formula downward. This one is going to be $B, $1 minus, now we're talking about looking at x3 and x0. This is going to match at x0, x1, x2, and x3, but we only need to think about x0 and x3, not x1 and x2. That's really nice. So I got to subtract the smaller one, the x0, times this number, minus B1 minus x3 times this number, all divided by x3 minus x0. See if those numbers seem right, 0.5227 and 0.5227 essentially. Matching these numbers, yes they are. Finally, just one more to go. Focusing on x4 and x0 now. So we subtract the smaller one times this number minus B1 minus this number times this number, and we're going, okay, I guess this goes on the next line, divided by the difference 0.8 minus 0.1. 0.52268568658. Yeah, I guess to that many decimal places these are matching. Okay, so that's how you could do it on a spreadsheet. And again, this is nice now because I can now go change x and everything will get updated. These numbers, by the way, this is your best approximation. And it is indeed of these numbers in the matrix closest to sine of 0.55 that is right there. I could try other numbers between 0.1 and 0.8. I could try 0.72 or something like that. And this number are now close. Yep, those are really close. I could try 0.43, 0.41687. Yep, we got a match there as well. Okay, so this is pretty nice that you can set this up in a spreadsheet like that. Not completely ideal, but still pretty nice. And I'd highly recommend working on that for your examples. All right, finally, I'm going to end by doing a sample exam problem that I gave in the past. This problem right here. You can see that the underlying function is the natural log function, ln of x. Our nodes are x0 equals 3, x1 equals 3.2, and x2 equals 3.3, so not equally spaced. And we're interested in approximating f of 3.1, natural log of 3.1, so the x that we plug in to Neville's method is 3.1. Show your work below the table that you see here, and then fill in the sparse spots in the table, and then circle your final answer, which you think of as your best estimate for the natural log of 3.1. Do notice that on this particular table I did add a column for x minus xi. I didn't have to do that, but maybe it could help a student if they're needing to be reminded that they need to use the fact that x is 3.1. So let's go ahead and work through this. So we want to fill in what goes here and here. You got to be really careful with this. This is really tricky. So let's go fill in what goes right there first. Notice that row I corresponds to 2. So with this labeling, we're after p sub 1 comma 2, which you could also label q sub 2 comma 1 to go right there. This is a Lagrange polynomial of degree 1 because it's going to agree with it at two nodes, 3.2 and 3.3, the first and second nodes. That's what's going to go there. So be careful. We start with x minus the smaller of the nodes, which is 3.2. X is 3.1. That difference is negative 0.1. And negative 0.1 goes first. Again, that would be 3.1 minus 3.2. Times, go diagonally here, times that number, right there, times 1.1939, minus x minus x2, which is 3.3. 3.1 minus 3.3 is the negative 0.2, times this number here, 1.1632, divided by x2 minus x1. 3.3 minus 3.2 is 0.1. I already did this one for them. I divide by 0.2, which was x1 minus x0. 3.2 minus 3. Okay, so this should give us, something you would hope would be close to what you see here, 1.13. And I mean, you can kind of cheat and see what the natural log of 3.1 is to begin with. We're hoping that we get numbers that are close to 1.13. So let's see if that happens here. Got negative 0.1 times 1.1939, which of course would be negative 0.11939, plus, two minuses make a plus, 0.2 times 1.1632. All that gets divided by 0.1, so we just move the decimal place over to the right. 1.1325, 1.1325, and yes, that is close to 1.13, so we're feeling pretty good, like we probably got the right thing there. Right, now let's do the one that goes here, which will be the one we end up circling, because that should be the best one. With the labeling here, which I'm not requiring my students to do this labeling, but just for your understanding, I is 2 here, so I minus 2 is 0. We're after P012, which is the same as Q22. Okay, so we're using nodes x0 and x2. We don't need to use node x1 here. X minus x0 is 3.1 minus 3 is positive 0.1 this time. Got to go 2 up here. Times the number we just figured out, 1.1325, minus x minus x2, 3.1 minus 3.3 is negative 0.2, once again, times this number, 1.1309, all divided by x2 minus x0 is 3.3 minus 3 is 0.3. So this should also be close to 1.13 and hopefully even closer to the natural log of 3.1. 0.1 times 1.1325 plus 0.2 times 1.1309 divided by 0.3, 1.1314 to 4 places after the decimal, and that does look good because here is the natural log of 3.1. We are pretty close. Okay, so that's a complicated method. It's very easy to get messed up. Okay, be careful, work hard at it. Thanks for watching.